this is a different kind of an event than we put on in the last 12 years. This is really one trying to encourage people to, in one discipline, which is making progress on sustainability and on energy savings and on helping the earth and making water safe, to be able to give their presentations for people that are doing other things at the university. So I wanted to tell you why we think that, as an introduction, they can all say I'm wrong, but I want to tell you why I think that water technology is playing and will play a greater role in expanding water supply. It's not going to make any water. There's a set, as I know now, I didn't always know, that there's only a set amount of water on the earth. It keeps on moving from water to air to back to water again. And more plainly, it's basically that we're all drinking dinosaur pee. That's it. The same quality. The
facto use.
yes, the quantity isn't changing at all. So climate change is causing more water to be transevaporated into plants and evaporated into the air at greater volumes. Thus, there is less water flow in water bodies, and there is more water being pumped out of groundwater basins. While we also have, however, a reduced water supply due to the pollution in our rivers, but in groundwater basins. So with less water being stored naturally in the snowpack of the Sierras, which we've depended on since California was settled, before it was settled, we now need to depend on our groundwater basins, and they're very, very polluted. The more that our groundwater is pumped out, recent studies by the San Diego Science Center of the USGS says that the pollution is more concentrated in the Central Valley. I would suggest it's probably true otherwise. So it actually increases pollution. So the most important thing is that polluted groundwater basins compromises our ability to replace the snowpack with another viable storage source. Storage for recycled water, storage for stormwater. But conventional treatment is expensive, really expensive. And the way it's gone in many places is that there's treatment train. Every time there's a new pollutant, there's a new add to the treatment train, and it becomes more and more expensive along the way. So just moving around the state, water around the state is extremely high energy using. It is the biggest use of energy in the state of California. Just moving water, the state water project, and other water around the state. So from my point of view, as a water policy person, any treatment innovations that remove pollutants more efficiently at a lower cost and lower energy use is really important. Any innovation that allows forever chemicals, and there seem to be a number of them, to be removed from usable water is critical. Any treatment innovation that reduces or eliminates the residual pollution left after water treatment is critical. Any water quality testing and monitoring technology that reduces the cost of doing the monitoring that's required is really important. This is why it's so important that everyone on campus that's interested in water looks to the School of Engineering, where we have some of the best engineering faculty in the world. It's really, I think they're going to be holding in their hands some of the solutions to water and energy sustainability and affordable water. And today we're going to hear from three who are designing technology that will make a difference in water resources and the water resources for our environment too. So with that, I'm going to move myself and move David Jassby over here, and I'll let you handle it from here.
Thank you, Madelyn. Okay, so this is, this is a presentation that it's a little bit of a mashup of a couple of things. What I'm going to try to do is talk a little bit about some of the things that we're working on right now in my group, some collaborative projects that I'm doing as well. And this is a slide talking about specifically about Los Angeles, which is, I don't know if we need to in this audience, everybody lives here, we all know the challenges associated with living here, but the long and the short of it is that in the next, few decades, we're going to be facing a lot of challenges to provide services that we come to expect in LA, in Southern California in general, water, power, clean air, and then of course, we have congestion issues, lots of them. We're trying to transition away from fossil fuels. We're trying to become more locally resilient in terms of water and energy production, and there's a lot of work to be done, which is also a tremendous opportunity to be involved in these enterprises. And if we, again, water is both a source of value, particularly in Southern California, where we don't have a lot of it, but we tend to use a huge amount of it. And it's also a limiting resource for other things. So, for example, it's a source of value for aerospace industry, for any kind of pharmaceutical or biotechnology production, any kind of manufacturing. And then it's a limiting resource in terms of resource recovery, agriculture, and even population growth at this point, which is what that glass of water is supposed to represent. Because we are starting to see now, not so much in Southern California yet, but we're starting to see moratoriums on new development of housing tracts, because unless they can show that they have sufficient water resources, and that's really a first, I think, in the U.S. It's happening in Utah right now, where local municipalities are not issuing new building permits unless the developers can show that they have I don't want to call it a renewable resource, but a consistent and a permanent resource of drinking water. We're starting to see issues. I guess the first one right now is in Florida. I know it's somewhat self-made, through the choices that they made over there, but communities are starting to run out of water. There's really some concern about that. We've seen this before in Southern California. Santa Barbara famously almost ran out of water in the 70s, and as a result, built the desalination plant, and then it rained the next day or something, right? So we do have a history here of water coming and going, and but there's always this threat of water scarcity. And from a person who is interested in water treatment technology, that presents a lot of opportunity, a lot of interesting problems to work on. But there's also a tremendous amount of challenges associated with that kind of work, which I'll talk about in a second. So what I want to do, Madelyn asked me to speak specifically about some of the things that we're doing at UCLA and in my group in particular, and Yoram and Shaily will elaborate on what they're doing. So I just took a selection of projects that I'm working on right now. It's not exhaustive, but I think it's some of the more interesting things that I'm working on right now. And I'll start with, I'll end with our desalination work, okay? But I'll start with some of these other things that maybe aren't as obvious. And so we have, so I'll start with lithium extraction from brine. Okay, everybody wants to buy a Tesla or switch their car. Those of you, and everybody in this room who doesn't have an electric car yet, which includes me, I know Yoram has one. Their next car will likely be an electric car, right? And there's a high probability of that, which is wonderful, right? It's going to minimize, CO2 emissions and all these great things. But we rely on critical elements, particularly metals, in order to enable these technologies, right? And so the question needs to be asked is, where do we get these metals? Where do they come from? And it turns out that metal extraction is a dirty business, and it's not just a dirty business. It's dirty on many levels, right? It's dirty, environmentally polluting, and it's also a dirty business from indigenous community exploitation. In some cases, there's slave labor involved, particularly in cobalt mines. So there's a lot of bad stuff associated with mining, and recently there's been a lot of also geopolitical tension around resource nationalism, and where countries are throwing their weight around and saying, well, we're not going to export anymore a particular resource that we control. And the first inkling of this happened a couple years ago, actually, between China and Japan, where China controls most of the rare earth element production, over more than 90%. And you may have no idea what these rare earth elements do, but they're absolutely critical we're making magnets, and these magnets go in electric vehicles and in wind turbines and all these things that we use all the time in computers. And it turns out that most of the production happens to occur, and the refining certainly happens in China. And there's a trade dispute between China and Japan, and China said, we're not selling any more rare earth elements. And there's a real concern in the US right now that this is going to increasingly occur. And so there's a big push in developing domestic resources. So if we're going to do this domestically, which I think is great, we have to do it in a way that is environmentally sustainable. So I don't know, I've been in the last couple of years working with a lot of mining companies, and it is incredibly difficult to start a new mine, particularly in North America. It's almost impossible. The lead time can be between, the shortest is about 7 years, and it could go all the way to decades, 20, 30 years. And after those 20, 30 years, you will never even get an operating permit, because the environmental impact report is so damning that the government will just say, no way, we're not doing this. So it's really important to be able to develop mining approaches to extract resources that are important for this energy transition, to transition away from fossil fuels, which is incredibly difficult. And one of the things that I got involved with is mining lithium from brine. So it turns out that North America, for example, has a lot of lithium. It's all over the place. It's not particularly rare element. But the problem is it's usually found in these very dilute streams. So hard rock mining, it contains, and there's a lot of mines in North America that contain lithium, but mining rock is dirty. It's hard, it takes time, it's very polluting. But we do have a lot of brackish groundwater that has quite a bit of lithium. Then probably the most famous example of that is actually right here in Southern California around the Salton Sea. The geothermal fields down there with the geothermal power, there's quite a bit of lithium. The trick, of course, is how do you get it out without spending a huge amount of energy and water and generating a lot of waste, a lot of pollution. So we are working on a membrane, which is basically, it looks like a little thin piece of plastic that will only allow lithium across the membrane. And this is a first of its kind material, and it's a completely new separation concept where it allows us to just pull out a single ion species from a mixture of basically an alphabet soup of elements in water. And we're going through the process right now of commercializing this technology. So we developed here at UCLA, we filed the IP, and now we start a company, we raise a lot of money, and now we're trying to build the infrastructure to manufacture it and form partnerships and try to do this at a scale.
This is something you're doing
Yes.
yourself?
Yeah. So that's ongoing right now. The other thing that I want to talk about is CO2 capture and sequestration. And then there's a reason why I'm talking about these things first and why I'm going to end with water. So CO2 capture and sequestration is probably the problem of our age, right? So our world is rapidly changing because of climate change, and I'm not a climate expert, but the experts, some of them maybe are sitting in this room, are saying that if we don't not just stop emitting CO2, but take CO2 out of the air at huge levels by 2050, we're in deep trouble. Like our planet is going to be a very, very different place, and Southern California is really a very different place. So there's a real imperative to do so. Question is, how do you do it? How do you do it cost effectively, which is very important? How do you do it without creating, knock-on effects of that other problems? So I'm involved with a group of my colleagues here at UCLA in developing technology, multiple technologies that can achieve that without using heat, basically. So we only use electricity, and the electricity that we're getting it from solar and wind. So we can do this CO2 capture and sequestration, and we're commercializing multiple technologies that can do this. All of these technologies are based off of very fundamental water treatment technology. So we're repurposing technology that already exists in sort of the water and wastewater treatment space, and we're repurposing it to do CO2 capture and sequestration at massive scales. And when I say massive, it's gigatons per year. So we're basically our entire planet is going to have to recreate the oil and gas industry in reverse in the next 20 years. Because they do about 10 gigatons a year of carbon extraction. That's approximately what they're doing. We need to do the same thing in reverse. Right? We need to pull out CO2 from the air and put it somewhere. Probably bury it or do something with it. Right? So it's a huge challenge, but again, a huge opportunity. And again, so this effort involves the commercialization of multiple technologies that were developed here at UCLA, and we've formed companies, and we've raised significant amount of funding, and it's it's an interesting ride. It's a lot of fun, and there's a lot of effort involved in this. So those are my two sort of technologies that I'm doing that have nothing to do with water treatment, but everything to do with water treatment, because they really borrow on the fundamentals of water treatment technologies to achieve these new areas of interest. And now I'm going to talk about these other more traditional water and wastewater treatment. So the extracting of energy and chemicals from wastewater. So this is the Department of Energy project that I'm part of, that I'm leading here at UCLA together with Princeton. And what we're trying to do is we're trying to convert your standard energy consuming wastewater treatment process and convert it to an energy producing process. Because it turns out there's a lot of reduced carbon, which is basically means there's a lot of electrons, available electrons in wastewater. If we can harvest them, we can do something useful with them. We do this already, to be perfectly honest. Right? This is what anaerobic digestion is. We generate methane and yada yada yada, and that's not new at all. What we're trying to do is to actually not produce methane, is produce a more valuable product, which is volatile fatty acids, so acetate, propionate, and butyrate and valerate, and those can be converted pretty easily to fuels. So it's difficult to do anything with methane other than burn it to make heat, because it's actually biogas in the case of wastewater generated methane, and that methane is actually really dirty, and it's difficult to use it for energy production. So it's usually just flared. We're trying to sort of move away from methane and make volatile fatty acids and hydrogen and ammonia and phosphorus and water, and big complicated process that we're putting together. And it's challenging and fun. There's a lot of very complicated biology involved in this, and that's very interesting as well. But this is a challenging process, and it's challenging because while we consider wastewater pretty disgusting, right? It's full of shit. But it's actually very dilute in reality, and it's hard to do something with something that dilute, right? It's actually mostly water in the end. So it's when you're thinking about, like, how can we create value? How do we valorize something like municipal wastewater? It ends up it's really difficult because there's not enough in there to make a difference. I did this. Oh, 3 minutes. Okay, so I did this exercise. Just one little thing. I did this exercise when we were writing this proposal. We were working with Exxon. They were our industrial partners, and the person from Exxon raised a good question. He said, "Did you ever make sure that there's enough carbon in the wastewater?" Because we were going to make jet fuel out of wastewater. That was our original concept. And they had to, "Did you ever make sure there's enough carbon? Forget about how you convert it, but let's just, if you just count carbon atoms, is there enough carbon atoms to make a difference in jet fuel consumption?" I was like, "No, I never thought about that." But in my mind, I'm just like, of course there is, right? There's no question. So we started doing the calculation, and I said, okay, let's take LAX. So it turns out if you collect every carbon coming out of every human in Southern California, every single carbon atom, and you convert it to kerosene, which is Jet A or jet fuel, can anybody guess what percentage of jet fuel you could replace in LAX? Again, this is not just from Los Angeles, all of Southern California. Anybody have any, like, back of the envelope?
All of it.
All of it. Less than 2%.
Gosh.
Less than 2%. So again, it's one of those things that's like, well, what's the point? There's no point in doing that. You're not solving a problem. So that's one of the issues with water treatment technologies is and I'll touch on that in the end. So because I'm out of time, I'm not going to talk about what
We have a minute or two.
Okay, I don't want to. We have a NAUI project, which is the National Alliance for Water Innovation. It's a recently awarded project where we're developing we call it a universal pretreatment system for desalination. It's an electrochemical based systems which allows us to, we hope, take any kind of water, wastewater, brackish groundwater, cooling, blow down water, whatever, and treat it to such a degree that we can easily then do reverse osmosis desalination on it and generate very little brine. So we can recover most of the water out of whatever stream we're using because of this pretreatment process that we're applying beforehand. And that's showing some very promising results, but we don't have time to really get into it. I just want to touch on the end. So there's a lot of treatment technology that are popping up all over the place. and they're popping up to tackle all these emerging water and wastewater challenges. That is absolutely happening. Things like emerging contaminants, which, Shaily's gonna be talking about, I'm sure. Desalination of seawater and brackish groundwater and surface water. Yoram is probably one of the, most competent people in the world to talk about these things. Wastewater recycling, which is what we're doing in Southern California. We're moving towards wastewater recycling. It's gonna happen all over the place. And then all these ideas of valorizing various waste streams, municipal wastewater, industrial wastewater, geothermal brine. There's lots of work on that. But there's a lot of challenge. So in order for this to occur, these technologies need to be commercialized. Somebody actually has to make a product, which means that somebody has to buy a product, right? And that's actually really difficult to do in this water treatment space because the industry is very conservative and the regulatory agencies are very conservative. So it's very difficult to get permits and adoption from the utilities. Also, it's very difficult to actually make a profit on these things because water is too cheap. The most difficult water to treat, probably the most expensive, is seawater. Right? It has a lot of salt. It's very expensive. I don't say it's the most difficult. It's difficult to treat. So desalinated seawater probably costs about 48 cents a ton. Maybe even less. They're saying now it's even less than some places in the middle of
Production,
Yeah,
it depends where, between 50 cents to $1 for 1,000 liters.
nothing. Show me a highly engineered, highly treated product that costs 50 cents for a ton. I can't think of a single thing. Right, so how are you gonna make money? How is a company gonna make money? Ultimately, we're trying to commercialize something. So it may be that the technology already exists for most things that we're trying to achieve. And really, it's a matter of public commitment towards spending that money to achieve our treatment goals. So it's not clear that you actually need any new technology to do a lot of the things we're trying to do. It's not clear. It's because it is a money problem. It's not necessarily a technology problem.
What about the conservative industry, and say a couple of words about that in the regulatory environment?
Sure, so a utility, before it adopts a new treatment technology, it has to make sure that it works, right? Because they're spending public funds, they have to raise bond money. It's difficult. You also have to get regulatory buy-in from the EPA or Cal EPA, or somebody needs to say, your technology works. That process can take decades to get approval. And for startup companies, which is really what a lot of people are talking about here, we don't have that kind of horizon. We can't wait 20 years for utilities to be convinced that something works. RO desalination was developed here at UCLA in the 50s. It took a long time before it was really, adopted. And it was part of it because, the technology wasn't good enough at the time. But it was also a lot of regulatory buy-in. People weren't comfortable with technology. It takes time.
And it's expensive.
And it's expensive.
When you can pump water for $200 an acre foot,
And there you go.
paying $2,000 an acre foot for $2,000.
Why would you do it?
But now it's not $200.
Yeah, yeah, it's 4 or 6 or 8. And eventually the lines will cross and desal will be the cheapest.
So actually, I would challenge this and I would say that it really depends where. So when you
Yes,
say
sure, absolutely.
it depends where, I can show you that water reuse, desal. First of all, let's define what we mean by desal.
Yeah.
Because desal is a technology and it's used for seawater, brackish water. Well, you cannot do water reuse without desal. So when you say water reuse, you're using desal, right? When you're purifying impaired groundwater, you're using desal.
Sometimes.
Well, sometimes if you want to drink safe water, then yes, you have to use it. So the point is that the cost really depends on where you're talking about. And the problem is that in California, some people don't pay for water, right? So you can't really fight against that, right?
What do you mean?
Well, there are riparian rights. There are people that, I was just in the city of Antioch, and I don't want to take from your time, where they can
This time
pump,
is over.
they can pump river water, without any constraints. They can pump as much as they want.
So our water rights system, I have a couple of quick questions.
Well,
for you.
he actually has the floor. He and Maria, both
Yeah,
are
go ahead.
here
I'll keep my mouth
outside
shut.
the university.
So
He's talking from the state water board point of view, and she's talking from the small water systems that are poor people and and from that point of view.
So I'm John Fish, I'm the chief deputy director at the state water board. So you talk about regulatory challenges, that's me. I'm the regulatory challenge. And so
Just get in line.
I have a couple questions about the things you were talking about, because it sounds interesting, but they also sound out, when you talk about harvesting carbon from seawater at a massive scale. I assume you mean you're gonna suck in seawater to do that. You're gonna suck in seawater, you're gonna kill all the life in that seawater. So how are you gonna keep the larvae safe? That's been one of the biggest problems with these ocean water desalination.
So two things I'll say. One, you can do beach wells.
Oh, yeah.
That fall.
Perfect.
You pay an energy penalty for that, but and save a lot of. Two, there was a recent study that was published, came out of Australia, and the Proceedings of the National Academy of Science. And they did a ecological survey of the ocean outfalls of the seawater of the brine from desal plants. This is very different than what we're talking about here. They found a remarkable increase in biodiversity in the outfalls of the seawater desalination plants. And that really, I thought that was a very serious study over a long period of time in a country that does a lot of seawater desalination. And it went through the peer review process. The results are pretty trustworthy, I think. And I think it really puts to rest this idea that if you do the diffuser, if you build the diffusers properly, you can mitigate.
I agree totally on the diffusers. I worry about the intake.
There's ways of mitigating that.
Yeah. Okay.
But it would be nice if you shared that article with me, anyone here that wants it, I would give it to you.
So I think that, this is my personal opinion. I think that there was a vested interest in the study that determined that diffusers cause shearing impacts to marine life, and I think that more study needs to be looked at that. I'm not sure that's true. I don't think it's an accurate problem. Another question.
You're gonna write it down because you have more time,
Okay,
okay?
great.
And Maria, any question for you?
Well, your technology sounds amazing. But there's a cost, as you said. So what about little communities in places like the Salinas Valley, in the Central Valley, in Imperial County, where there's a great need for them to have not just, drinking water, safe drinking water, but also deal with their wastewater. A lot of them don't even have septic tanks, they have cesspools. So I guess has your research taken the costs into account of maybe being able to put these in these small systems like the mobile home parks in the Coachella Valley, where Coachella Valley Water District is, now supposedly hooking them up, and I say I'm using air quotes, they're just starting to put the backbone infrastructure. They're nowhere near being able to connect them. So maybe like a package plant that, Yoram is working on.
So I think that you raise a super important point, and it's absolutely valid. And it kind of touches on what I said, that I'm actually not sure that we need a technology to deal with these kinds of challenges. We have technology that can treat nitrate, we have technology that can do very small scale wastewater treatment very cost effectively. I'm not sure we need a new widget to do what you're talking about. It's about cost, right? And the reality is, and Yoram will probably publish a definitive article about this, that if you look at the energy consumption, which is really the main component of the cost, not the only thing, of desalination technologies, we're very close to the thermodynamic limit. It means there's not a whole lot more room we can go. There's just not too much improvement we can achieve by a new widget. So these kinds of communities need financial help. They don't need a new mousetrap to do the job.
But in some ways
Unfortunately,
they-
the governor vetoed the bill to do exactly
Right, but
that.
see, in many ways, they do need a new widget, because even the technology, a lot of them, you're gonna have challenges with having operators. And in those communities, even in urban LA, and I've worked in urban LA, I've worked, one of my clients is a water replenishment district of Southern California. So they have big pumpers and they have little tiny pumpers, and I work with those operators. And what you're talking, and I know that this isn't meant for those communities, but if these technologies could be somehow made so these communities can benefit, because you're gonna put public dollars in there. I'm assuming that, you know, a lot of your work is based on grants,
So,
and so it would be, interesting to see how these people
So,
can benefit.
Maria, I think what we're talking about is there's technology that you develop.
Right.
And then you want to know if it works in the real world, and then how do you make it so that it will be economical and operable? So then we talk about operation and maintenance, and that's another layer. I'll
Right, but
talk about that a little.
Yeah.
Right, but
you're
that's
taking
critical
time to talk,
because,
right.
Yeah, I'll talk about that.
right, but that's critical, and the reason I say, and you know, I build those treatment plants,
Right,
they're
right.
conventional, they're nothing brand new.
Right,
And even then, the operators, you know, to even something as simple as the OMMP, the operations manual,
of course.
they have problems understanding it, and that is,
amazing work being done in automation of a lot of these systems.
All right, well, I'm gonna have
Okay.
to stop this really exciting conversation.
I'll say one thing, just one last thing.
Yeah,
So I gave two examples of water treatment, and then I gave two examples of like this new carbon-free economy thing. And I can tell you from experience is that if you're trying to commercialize technology, commercializing anything that doesn't have to do with water is so much easier. It's dramatically easier. And then trying to commercialize with anything with water is really difficult. And it's almost, even though it's basically the same technology, literally, the same thing. We're just, one of them, we're making water, and the other thing, we're making something else, that's not water. And it's just,
I think,
that's the only difference.
I think,
so that's all about the industry.
Yeah.
And-
It's about it.
Investors.
right, well, I think that
Thank you.
commoditizing water needs to be.
This is Shaily Mahendra.
Shaily Mahendra, I'm colleague of David's, who's a colleague of Yoram's. And Mike, and lots of familiar faces in the civil and environmental engineering. I'm a civil engineer turned environmental engineer, turned microbiologist, turned molecular biologist, and a few other things in between. So when I was hired at UCLA, was looking at understanding and controlling emerging contaminants in water. And for all postdocs, grad students, early career researchers, always good to think of something that's emerging, because that's like job security. There's always be something that is emerging. Either you find more problems and then get to do more solutions. So it's a very dynamic way of researching something that's always latest. May not always be the greatest, but definitely the latest. And one of the earliest things, the other thing that you have to do as an early career researcher is not do the only thing that you know how to do, which is your doctoral research. So you have to distinguish yourself from your former advisors. And by that time, this is all you know, and you can work on it. So that was my motivation, to sort of look around, read papers, see what something that my amazing doctoral and postdoctoral advisors, I worship the ground they walk on, but what is it that they're not doing? And what could I possibly do? Things that others haven't thought of. So then you go big or go home, right? So I went bold and figured, okay, this seems to be something that's emerging. Not many people know about it. So any little incremental learning that you do and share with the research community, practitioner community, is going to be valuable. Hashtag tenure. And and it'll still make a difference. And I'll grow as a scholar in the way, even if this doesn't work, something else will, but the approach would be nice. So I started reading review articles and just emerging things about this class of chemicals that are called PFASs. And they were called other things. It's such an alphabet soup, abbreviations there, but things that are carbon, fluorine containing organic chemicals, and they're found in firefighting foams and pesticides and non-stick cookware and metal suppressing and hydraulic fluids and all kinds of things, surfactants, mining. And I figured, yeah, okay, so I did work on understanding carbon fluorinated organic compounds, brominated organic compounds. What could possibly be hard about fluorinated carbon? And I happen to have some friends who worked at DuPont and other places, and they're like, yeah, this is going to be a big deal, but don't worry. couple of decades ago, there were these ozone depleting chemicals called chlorofluorocarbons that were used for refrigeration. So it's just going to be similar. Sounds like a good idea. So I started learning more about it. So these are organic compounds. Carbon fluorine bond turns out is one of the most strongest bonds. Covalent bonds, even stronger than carbon-carbon bonds in diamonds. So now that these chemicals are called forever chemicals, and I'm like, no, diamonds are forever. These chemicals are not forever. If I have anything to do with it, we'll definitely make some changes there. So there's a whole tree that's like different abbreviations depending on what kind of groups are there, or how many carbons, how long is the chain, it's hydrophilic, hydrophobic, all kinds of things. They're being used everywhere, and they're very valuable in intended uses. I mean, it's amazing. Whoever, DuPont, 3M, BASF, Chemours, whoever made these, definitely had a good industrial reason for it. Something that puts out fires and saves lives, what could possibly be not right about it? And, just like other oops moments we've had, DDT kills mosquitoes. What could possibly be wrong about it? Yeah, 15 years later, we find out Silent Spring and all that. That everything that we think is going to solve a lot of problems sometimes creates more problems. But more research opportunities. So these fluorinated chemicals, they are associated with a lot of health effects. So do understand the health effects are different depending on the recipient, whether it's humans and different compromise or other humans. I would totally consider myself, whatever is the most vulnerable, count me in that group. Whether it's ecological health, birds, snakes, rats, whatever. And how they're being exposed to water is one thing, and which is, I'll try to keep much of my research focused on water, but there are many other ways to get exposed. I mean, we tend to use our non-stick coated cookware way longer than we should, and chip, and I would never be able to look at a bag of microwave popcorn the same way again now that knowing what I know now, that I didn't pizza boxes and lining up cans and plastics and everything. So it happens. And like Professor Jassby said, yes, our real problem is there's too much water and not enough pollution. So this is our target. This is really our target here. What's currently being proposed by the federal EPA, and there's some state guidances that we're talking about nano picograms per liter, which is a drop 1 in 1,000 times. This is, I just learned it's such a powerful statistic to know. Here Ramos, who's defending her PhD next week, pointed out 1 part per trillion is about 1,000 times smaller than a drop of water in an Olympic size swimming pool. So that's what we consider safe. Anything more is a health problem, all kinds of health problems. Some of these, so notice these are class of compounds. Some are more toxic than others. It just could be that they are better studied than others. They are classified as hazardous substances. Understand not everything is hazardous substance everywhere, and there's a dose, of course, this chair is probably not very hazardous, but if I eat 10 a day, maybe I'll have some health effects. So it's also about the dose and response. And as you can see, these doses are getting scarily low, enough that we can't always even measure them. I talked to the directors of analytical labs, and they're like, we can't get water clean enough to serve as blank, because there's so much more. You send me a contaminated sample that turns out to be cleaner than my blanket calibration standard. And a whole bunch of other things. So this is definitely one of the emerging contaminant classes that I research, and I'll focus on this. 1,4-dioxane, MTBE, synthetic dyes, microplastics, antibiotics, pharmaceuticals, munitions, chlorinated solvents, and a dozen others. Those are all things that I research. But this seems to be very interesting and relevant for the water research. So in my lab, generally, I would say in collaborations, obviously we're not doing it all alone, but in collaborations with colleagues, such as Mohanty, Jassby, at other academic academic institutions here in the US, Canada, China, Japan, Australia, members of the Department of Defense, Army, Navy, Air Force. I actually have sponsors and collaborators from there, and engineering consultants and companies that make them. Which is kind of nice to get grants, but every once in a while I get called to essentially serve as expert witness, and I'm like, if it's anybody of these, then I'm sorry, I have a conflict, because I get funding from them. So getting funding is good, but then it puts me in, try to keep the science as independent and objective as we can. So in the actual environment, we try to understand how they move in the environment, how they're retarded, and how do they line up in the interface? That they tend to be getting away from water, part of it's dissolved in water, which is what makes them very valuable for their non-stick properties and other things. Everybody I talk to, they're like, these things are not biodegradable. I said, yeah, but that's what we said about NDMA. That's what we said about perchlorate. That's what we said about PCBs and something else. So eventually we'll figure it out. There would be some biological reaction. And again, the food that we eat is technically not digestible. Can't pull up a tree and eat it. Sometimes we need to chop and cut and blend and boil and other things. So there may be treatment trains, as Madelyn mentioned, might be valuable. But we should still understand the individual technology. So I use a lot of biotransformation related research on enzymes, bacteria, fungi, other things. And then when it comes to non-biological treatment technologies, I use high frequency ultrasound, something just a little bit lower than sound frequencies that you get if you get an ultrasound at a doctor's office. And a little bit higher frequency than your aromatherapy diffuser at home. So really not that bad, but yes, it will require energy and other things. We also develop sorbents, modified activated charcoal sorbents that would help, and then various catalysts that with or without light or with or without current, they can degrade. So I call them, these are the best ways of achieving PFAS removal. That usually gets people's attention, but best is really just an acronym here: biological electrochemical analysis technologies. So you see the cartoon on the left, and that's just an electron micrograph artificially labeled with fungi. We have a lot of fungal experiments in the lab. Electrochemicals, working together with colleagues, they develop these magnetic phase, titanium oxide, and other catalysts and electrodes. And then this is a picture of looks like a deep fryer, almost ready to take on French fries, but this is actually a sonication bath. We developed 2 or 3 technology versions in the lab. They were about 1 liter size. And then the US Navy liked it so much, they wanted us to make a big one. And then we put it on the back of the trailer. And it's been going up and down the California coast. Last I heard it was in Port Hueneme. I was hoping to get it back for research, but they're like, no, we own this equipment, we're going to keep this. But there are other applications, not just the PFAS, but other water contaminants that could break down.
3 minutes more.
3 minutes more is perfect. Yes. My students and I love to travel, and we go and collect samples. Everybody else goes to Orlando, to Disney World, and we go to Cape Canaveral, and and those rockets take off, they burn a lot of jet fuel. And those fires have to be put out, so they get sprayed by these aqueous-film forming foams. And after a while, all the news cameras go home, rockets out in the space, and then all that foam just percolates.
So just
into the
to clarify, you're talking about the fact that we haven't stopped using PFAS containing. No,
Not even close.
not even.
Not even close. And I have friends who are captains of oil tankers, going all around the earth. They're like, oh, what my dead body. I'm in the middle of the ocean carrying, I don't know how many million gallons of benzene, and there's a fire. I'm going to need something that works. So until something equally good or better is around, not getting rid. But there is legislation that's emerging. Some of the previous older stockpiles need to be destroyed, and some of these technologies might be helpful. Yeah, so we collected soil and water from various places, and we isolated a lot of bacteria and fungi. That's what microbiology labs do. And we think some of them have potential to actually biotransform some PFAS. Not everything, not like you blink and the whole big monster molecule of PFAS is gone, converted into carbon dioxide. That doesn't happen, but slowly and steadily. And we have, like I said, over 100. To make sure that my students graduate within 4 or 5 years, I ask them to pick their favorite 6. And Nancy picked all the pretty ones. So she's like, I'm gonna take all the pink and purple ones. That's as scientific as a reason to down select as any other. And they work really well. And we're doing more work with them, and Kshitija and Ethan and Himadri and others are looking at how we've done that. This is just an example of how you can have PFAS in the groundwater, and as you can put in trenches and put electrodes and maybe create DC power from solar cells and to be able to serve as a barrier treatment technology. This is also being used in places in Colorado and Wyoming and elsewhere with my colleagues doing field work. Pia's work was to take granular activated carbon and then modify it with cationic polymers. So long chain PFAS is anything that has more than 8 carbons can adsorb to carbon charcoal pretty easily. The short ones, not so much. But then they have this most of them have a negative charge. So we just lightly decorated activated charcoal with these cationic polymers. They're very safe. They're used in water treatment. And so if you can catch the molecule from the tail end, great. Not, let's catch it from the head side. And that worked reasonably well. And now we can use it to concentrate so that we don't have too much water and too little pollutants, and then destroy them, and then use same kind of ultrasonics and other technologies to break them down. Speaking of ultrasonic, a small bubble. So if you take a water thing and it bubbles, the inside temperature of a bubble, the air inside that bubble could go up to 5,000 degrees. So that really just breaks every bond there. So it's an energy intensive process, no doubt, but every once in a while it comes in handy when you're treating RO brines and other things. Or you can combine treatment training. Give 30 days for the fungi to do their job, and then another 4 hours for ultrasonography to just clean it up, polish it up. Basically, what I wanted to say that will be required to achieve pretty low cleanup levels for public health protection, of course. Biology has to be part of it because large volumes of water, river water, soil wastes cannot be, you cannot put a big ultrasonic probe and shake the planet around. I personally like fungi very much. They're extremely good looking. Electrochemistry works. There are concerns about the cost. Ultrasonic works, again, there are certain places where they're more useful than others. And like I said about example of cooking, you might need a combination of technology. That's it, yeah.
So
Thank you,
I'm,
people who take us, yes.
Maria, you're on first. Any questions?
I wish the California legislature would have contacted you before they enacted the bill.
The bill, explain.
Yeah, they are working on it. yes.
Well, no, they have, it's already in effect. So as someone who works in disadvantaged communities and deals with contamination, one of my frustrations, because I've been involved with the attempt, and to be honest, I really stay away from PFAS. I'm already in over my head with iron and manganese. I don't need any more contaminants. I don't know how to solve that, but we need to work with you guys. The legislators need to work with you guys because what they do,
What did
And
they do?
they enact legislation, they said MCLs,
No, before the science caught up.
yes, and then,
For the science stuff.
They have consultants.
yes, who are not scientists or engineers, and I've gotten on their case because I'll give you a good example. This will play into what you do in Maywood, and John is familiar with my Maywood project. The MCL was set in statute in AB 890. Before we had a treatment. I mean, there is a treatment, it's green sand, but the vendors, when we started, the design and building the project, no vendor wanted to go to non-detect. They didn't, and you're talking about the industry. Well, they didn't want to even get near it because they didn't want to be held liable for that MCL. So I mostly have a comment. I wish that legislators would consult with you guys before they set legislation, because then someone like me is stuck pulling out my hair literally, trying to get these vendors to at least try to meet that MCL, and they're saying, no, we don't want the liability. And that has nothing to do with state board, that's with the other side of that park.
Well, I mean, it's always a mistake for legislatures to put in, science.
So they didn't
That-
wait for you guys to go through your process at all.
No, it's such a tennis match when you put analytical chemists and engineers and toxicologists. Because the chemists would say, this is what we want to, these numbers, diminishingly low numbers. And toxicologists like, wait, but we don't really know the effect of this on that.
And then political
And then,
science,
and then
scientists write
political
the-
scientists, and then
write
people
the
like me,
law.
like, once you figure out what the problem is, all the engineers.
but see, that's the issue, is that there's, you know, and I don't know what the solution is, but I really think you guys need to be more engaged in these processes. So that will, Yoram was like, now what is she asking for?
Well, John, go to you. Does the board have, the air board has an outside technical advice, expert advice on
So-
universities? Why doesn't the state board have access?
Because it's no money. There's really the air board got, money from, I won't remember which, or I think it's the license plate, directly for research. Because somewhere along the way, the legislature decided that air stuff is really difficult and water is really easy. And so, they gave, this research end. We don't have a research end, but we do have, you know, for MCLs, what we have is we have OHIA, the Office of Health Hazard and Assessment. And so with them, we get the first part of that, which is the public health goal, which is essentially looking at what the problem is. Then it goes to us in our drinking water folks to look at how can you set a maximum contaminant level that is as close to that is achievable, which is the nice thing. I mean, I think that's a smart way to do it, because it lets you use the public health goal, but it also lets you look at, is it achievable to do this? Is there a way to meet this for most of the water systems? And that's what you miss if you have legislature come in and set a goal. I had a quick question for you on, you talk about pulling some of this stuff into carbon or use, and is that carbon able to be regenerated at a hot enough, temperature to destroy, or are we just moving it to the air to be, and then drop down again?
A bit of both, so carbon, any carbon that's saturated with gases will not be accepted at landfills. So you can only burn it at coal-powered power plants. Some of the other technologies, including ultrasound and some other methods, steam regeneration, can partially destroy gases on it.
Because, I worry about, us just moving it from one place to the other.
Yeah.
I think the only real way that so far we know to definitively destroy PFAS is through incineration,
Incineration. is the only-
high temperature.
High
incineration.
temperature.
1100 or more.
Yeah, so, yeah, with lots of oxygen. And just get it hot enough and it'll turn to CO2 and.
Yeah.
But that's really, I think. Probably the most cost effective way of doing it too.
And so that.
Well, how do you get it to that? Do you do it through carbon?
Yeah, through carbon, and then you just burn the carbon.
And then it also helps to concentrate.
Yeah.
So there's nothing wrong with it, like it's one of one part of the treatment. But in North America, incineration is more accepted. In Europe, it's not. Carbon is still accepted.
So,
And then they probably have more space to landfill it, or I don't know what it is. But here, I think it's good.
All right, well, thank you.
All right.
The next one is going to be Dr. Cohen's. And I have full disclosure, both Maria and I working with him for quite some time, so we'll correct him if he says anything. Let me just see if I can get rid of this here.
There's the bigger thing is they're also immunosuppressants. There's some really distressing research emerging that places that already had PFAS impacted communities had higher rates of growth
Really interesting.
and lower effectiveness of vaccination. It's really bigger than that.
But how do I get that?
Some of the new NIH and CDC data. Prisons, for example. Prisons and immigrant.
All right,
Located in places.
we're on. Thank you. You guys.
Well, I thought I was gonna give a certain presentation, and then I saw the list of questions. Madeline, and that scared me. I'm Yoram Cohen. I'm in the chemical and biomolecular engineering department, and also faculty member at the Institute of the Environment and Sustainability. And what I'm going to tell you today is about, in a pictorial way, more about examples of some of the things that we have done and are doing. I'll say a few words about elements that I'm not going to describe in terms of examples, but the important thing for me to tell you is that, you know, California is our playground, right? I always say that there's a lot of water in California. Unfortunately, a lot of it is saline water. We also have a lot of groundwater. Unfortunately, in a lot of places, groundwater is contaminated. I'm just giving here an example of nitrate in many wells that is at or above the MCL at some point, you know, during the monitoring period. So everybody already talked about drought conditions, climate change, the fact that we have to deal with various elements of the water portfolio that we have, and Maria talked about rural communities that have limited access or to clean water. And one of the things that I'm going to talk about today or mention to you is that of distributed water systems, for treatment and desalination. And I really think that this is going to be a paradigm shift. You know, a lot of people talk about decentralized. I hate this word because to decentralize means that you need to take centralize and then decentralize it. But here we're talking about things that are really have never been centralized, and so they're distributed, and we have to reach a lot of different places, communities, and in fact, even in industry where the treatment systems are not connected in any way.
So there's no treatment, it's just the places.
Right, and so the issue is, what is the state of the art? So as David mentioned, yeah, we have a lot of technology, okay, already. But the problem is that when things are distributed, there's no operator 24/7 at each location. So you have to figure out how to make those systems more intelligent, right? So they can run on their own, they can be self-adaptive. And so really this is the goal and the conclusion of my presentation is that we need intelligent water systems for treatment and desalination for distributed deployment. And can we do it? The answer is yes. My talk is over. Okay, all right, but
Can we have some wine now?
It's there for that reason, you need one.
so in my group, for the first, so you see the backdrop is California behind it, but I have photos of a few systems that you will see in a minute. So what I've been doing over the years, well, first I would say for the first 20 years of my career here at UCLA, I thought that I knew everything, and I was studying problems. And then in the next 22 years, I sort of realized at the beginning that there's a lot that I don't know, and I can actually use it to solve problems. Okay, and so that's what I have been sort of the adventure that I've been going through. So we've been making membranes, we've been doing salt harvesting from brine concentrate, developing various theories of wonderful systems. But today I'm going to tell you about what does it really do in the real world. And can we make a difference? I'm not gonna talk about money and how much we can earn from it. And you guys can, think about it, and if you're interested, you can go to the UCLA Office of Technology Development and license all the patents that you want. All right, so the first one that I'm gonna mention very quickly is, development for the US Navy. And this is an integrated system for water desalination. It also has pre-treatment. And as David, said earlier, pre-treatment is very important. And in fact, in what you see at the top here, this is the pre-treatment and this is the desalination. So you see the pre-treatment is much, much larger than the desalination. It has many, many elements to it, and I won't go through all of it. The primary is ultra filtration, it has coagulation. The whole point is that the US Navy wanted to have a system that is small enough, can fit in basically a marine going vessel, or I would say on a frigate, and no containers of any kind. So the two systems talk to each other directly. There are no feed tanks, there's no nothing of the sort. In any event, so UCLA, we developed it, and it's patented, used by the Navy. And the most important thing in here is that the Navy wanted to have a system that can run for up to 6 months without them having to have any, chemicals or an excess of chemicals in order to treat the system. Or to having to clean the system chemically. So I'm just going to show this, and this is what happens when you're in the real world. The system was run at Port Hueneme, is that we were working there and there was a storm. We knew that the storm was coming. So we have a specialty controllers that we've developed. And here you're looking basically just at the backwash efficiency for the ultra filters. And you see that at the top, you see turbidity and chlorophyll in the red. That are beginning to rise as the storm, gets closer. Yes, that's seawater. That's seawater from an open intake. So what happens is that the membranes get fouled, and then the efficiency of cleaning them, begins to drop. So at that point, when the storm starts, we activate the controller, and basically, this is for David. It basically increases the coagulant dose. Okay. It increases the coagulant dose. You see the efficiency of cleaning or backwashing the UF membrane, which is before the RO, increases. And then when water quality improves, then it decreases the coagulant dose. And that's important because that means that they can save on coagulant dose. All right. So that was a nice adventure. And I should tell you that in this part, we were so excited, and we told the Navy that we have a wonderful theory, which David mentioned earlier in a paper we wrote a long time ago. We developed a theory for optimizing the energy consumption, and we said we can do that. And the Navy, there was I forget, he was a lieutenant or the general, whoever it was, said, "No, we're not interested." And I thought, what? We did all this work, and we have this great theory. And he said, no, pre-treatment, energy, it's 1/1000th of the energy that we use goes into the treatment. So don't waste your time, right? So you learn about it in the real world. The next one is agricultural drainage water. So putting all the different theories for control and optimization in order to treat agricultural drainage water. This is actually in the Panoche Drainage District. And one of the challenges in there is that water quality changes with time. It changes when they irrigate because they draw, the brackish water here is really from a shallow aquifer.
Explain why agricultural drainage water is so important to treat first. What is it so that people who don't work on farms know that it's what's coming off?
The salinity builds up to the point where you can't really grow. So what they grow is switchgrass, up in the San Joaquin Valley, which they use for feed, or they put the high salinity water in certain areas, but it's limited and time is running out. So what happens is that in this whole area, there is very poor drainage. So you have a lot of water that is coming in from the Sierra, from the Delta. There is a lot of evaporation, in this area. And so the salinity increases. So what they do is they over irrigate in order to, to wash it and then collect it in drainage canal. So the question was, can we take this water, that you see in here, right? How many of you would drink this water? No one. Okay. So, so this is the feed water. It's about the top salinity is about 20,000 milligrams per liter. Seawater is 35,000. Okay. So it's pretty high. It's heavy in nitrate and all sorts of other things. So in this particular case, we take the water, microfilter it. It's still greenish. You wouldn't drink it. The UF filtrate in here, and I know that David, you do a lot of work on coagulation, and we'll back up. What I'm saying is that even with filtration with coagulation, you can remove a lot of the contaminants in particular. And this is the water, okay, after the hour on. Okay, I drank it multiple times. I'm still here. Okay.
Drinking.
Well, could be. And we treat this kind of water. The point is that the technology is there. The key here was the optimization, so the system can change its operation depending on the water quality and as it's changing, and how to put it into a much smaller, basically footprint that you see in here.
So Yoram, can I ask you a question? So
Sure.
what is, sorry, talking about
What's the key here?
Well, how much does it cost? What's the cost of the cubic meter of this kind of water?
It's a good question you asked. Actually, there's a paper we published some years ago on the cost analysis, and it could be all the way from about $400 an acre foot, to $800 an acre foot. It depends on the water quality, because it changes in here. And the important thing is, what is the value of the water? So you can't just do the analysis and say just what is the cost. You have to ask, what is the value of this water? If the value of this water, in terms of the value to me, if I'm a farmer and it's free, I wouldn't want to pay. On the other end, if you have farmers, when we had the drought, we still have the drought, but a number of years back, we were paying up to $3,000 an acre foot. Okay, especially if they were drawing it out of the water bank that I don't want to mention any names. Then
Mention names, it's all okay. I have a quick question for you. What are you doing with Brian? You're in the
Okay.
Central Valley. You don't have any.
Yeah. So in this particular case, remember that we're taking in this particular system, in the Panoche district, they had a particular area for it. Plus, we developed, and I'm not going to talk about it now, is actually brine management. So we actually take the brine, we self-harvest, we remove gypsum, from it, which is the major thing. And we can go up to about maybe 93, 95% recovery. You'll still left, with a little bit. And I don't know, David, if you mentioned that now there are efforts on a national level, to deal with the brine. And the key is to decrease the volume. If you decrease the volume, to 5%, maybe 10%, then there are all sorts of elements, all sorts of treatments that you can do.
So,
In this system, since this was an experimental system, you take the water from the drainage canal and you put it back into the drainage canal. So, you're not really having any impact. Okay.
You have 5 minutes.
All right. Now, the next one is remote communities that are smack in the agricultural areas. So there are a number of issues here. Their water usage changes on a daily basis, on an hourly basis. So whatever treatment you put in has to adjust. Number two, they are not able to manage their own water system, so they have to be self-adaptive. And so this is a lot of effort that we put into it. And you have to meet regulatory requirements in those communities. Their water is above the MCL with respect to nitrate, and it's also high in salinity. Okay, roughly at about, in the examples that I'm giving you, about up to 2,500 milligrams per liter. So 2.5 grams per salt. The water that you're drinking here in LA is about 0.2 grams of salt per liter. Okay, just if you were wondering. Okay, so we have 3 communities. Basically, I already mentioned that there is an issue about the variability. We need to make the system smaller, so the footprint will be reasonable. We have to deal with a discharge in it, and so an important part of that is demonstrating that nitrate that we remove can actually be put into the septic tank, and under the anoxic conditions, it actually gets denitrified. Okay, so because of that, we were allowed to actually put the concentrate in there. So
just to make sure they understand that this, how important this is. If he gets a permit from the regional water board to put this brine back into the septic system, it will be the first time that the board has given such a.
So actually the system, so what I'm going to show you here, I'm going to go very quickly through this and show you, here's a system. Okay, this was all designed and built by by UCLA. Certain elements where UCLA was involved in building. We had contractors, and what's unique is this system operates in the mode of concentrate recycle, so we can actually have a nice footprint in there. You see the tanks that are here to actually have the product water, pressure tanks for the community. This is the system which I can operate, manage from my smartphone. Okay, in here, and as I mentioned, the challenge is that this is the water usage during the day. So the system needs to know how to adjust. It works part of the day, and then it's dormant through other parts of the day. And we develop a whole cyber infrastructure for it, where we monitor those systems remotely. I'm not going to do it here. This is, if you click on any of those sensors, you'll see the data, the current and historic and so on. And so we're actually using it now as part of a major project with the National Alliance for Water Innovation to actually develop models that will allow us to understand the operation of such system in the real environment, and basically forecast, their operation, and be able to tell from afar which sensors may not be working properly. So I'll finish with, showing you what I mean by the operation of the system. The regulators say the MCL is 10 milligrams per liter, nitrate is nitrogen. But the regulators that we work with say, no, you cannot exceed 8. Now, that's not written into the law, but when you deal with the real world, that's what you have to do. And you cannot argue and say, I'm not going to do it because, the regulations say 10, right? So you have to design the system so that when you're approaching 8, the system will automatically, divert, the product water, into discharge, as an example. And we wanted to be able to forecast it, but I'm not going to talk about it today. So we developed various machine learning type models with AI that allows us to do the forecasting. But basically, it means that the system is off for a period of time, on for a period of time, and that all depends on the consumption. So it's not just the treatment, but this is for a complete, system. Those systems, this one that I'm showing you has been operational since July 2020. So we actually started during the pandemic. And since we were in the field, we were actually had permission from UCLA to actually travel, to the field and do the work. There are now 3 systems that are running, and this one just received, a complete, bill of health, and the residents that were on bottled water until now, are no longer under this constraint. Okay, and so this is an example of what the technology at UCLA, which I skipped over. I didn't tell you about all the fine details, right? Of theories for control, theories for energy optimizations, how we developed, an approach for nitrate sensing, looking at nitrate versus salt passage, and how we can tell, whether a nitrate sensor is not working properly based on what we see in the salt passage. So, but the point is that all this technology, that we have developed over time and patented has actually gone into the real world, into the real field, and providing water that people actually drink. And this is, the beauty of being at a university. For all of you who are starting your work, is that enjoy the science and the basic fundamentals, but also always look into the fact that you can make a difference in the world. And this is a great thing. And for water, I can't see any better way. I always say that water is where people can cooperate, not just regionally, but on a national and international scale. So I didn't talk about business, because when I'm at UCLA, I don't talk about,
I do talk about business to bringing this out, this beyond the pilot project.
Well, the major thing that I've learned, and for us scientists and engineers to learn, is how to walk the line between science, policy, and the regulatory arena. We can't assume that just because we have the science or the technology that we develop, that it will be automatically adopted. On the other hand, regulators and policymakers, also have to understand at times, just because they mandate something, it doesn't mean that the technology is there for it to happen. We heard about that. Okay, so that's really key. And so here, there are multiple stakeholders. There's the county, there's the Water Resources Control Board that really funded the work with the disadvantaged communities. But there's also, the county, the Monterey County. There's the California, and the local, departments of health. There is the drinking water division, and you have to satisfy, everyone, and also their job, and maybe it's not easy for technologies to understand, because it creates a lot of constraints, but their job is to make sure that the public is protected.
You don't screw up.
And you don't screw up, exactly. And so you have to accept that and work with them. And I have to say that it was hard for me to do that at the beginning, but I came around to understanding their viewpoint. I've worked with the US EPA for many years. I was on the Science Advisory Board, for the US EPA, but that was different. That's because I was there and I was, informing people what it is that they should or shouldn't do. But now this was completely different. I was put on the spot, and often you feel like you're just, you just finished college, right? Because they come with all the questions and the demands, and you say, "Well, you're asking me all of that," But you have to do that. So
Thank you. So we're going to turn off the slideshow now, and we're going to ask John to say a few words about all three presentations. And from the point of view of both the funder, you run the Department of Financial Assistance in the board, and the regulator. What's your perspective on how to develop this kind of technology, and create a closer link between technology developers and how they can bring their technology into how can we help you get money so that you can actually get scientists involved in your work?
So let me give it a try. I mean, as Juan said, said that it was hard to deal with the regulators. Probably the regional board was probably one of the hardest, but our division of drinking water is also hard. And you have to recognize that that there's no incentive for them to take a risk. They don't care if you're not going to make money on a product. It doesn't matter to them. What matters to them is that the technology is repeatable, verifiable, And that it works every time. You've all seen the papers about Flint, or about, it doesn't matter if 999 times out of 1,000 it works. The one time it doesn't work, it is on the front page of the newspaper, and the regulator is blamed. And so they're very conservative folks, and they should, because what their job is, I'm talking about the drinking water people, I'm talking about the wastewater people, and their job is to make sure that people never get sick from drinking their water. And I know that, we can talk about it. There are lots of people that don't have safe drinking water right now. And these technologies might help them get safe drinking water. And so our folks are very cognizant of that. But it's easy to explain that the local community can't afford to treat their water. It's not easy to explain that we invested state money in a project that worked really well until there was a breakdown, and then a small child got sick and died. And so there is this whole issue of being able to show not that you can do it in a university setting, but that you can do this in the real world, in real conditions, as the flow goes up and down, as the concentrations go up and down, all of that. That is the level. Madelyn asked me to talk about moving some of these things from research to production. The only real area that I've dealt with that is in the monitoring side. We worked with labs around the state to move cell line bioassays from a research kind of component. We were looking at estrogen compounds and how that impacts sediment. And what we saw was that there are lots of estrogen compounds out in the environment, in the wastewater there. And how do we best address that? We looked to cell line assays, but at that point, they were all individual university projects. Different people had different ways of doing it. So we worked with manufacturers, we worked with scientists to actually take that until we got to a point where they could be reproduced at the different laboratories on I can't remember the term that they used, but they sent it to different labs. They all use the same methodologies. We refined the methodology so we could get comparable results. We actually now are using these in a regulatory context around the state, looking at the estrogen compounds that are going to the next cell line assay. But what it took was repeatability, consistency, and lab comparability for that to work. I wanted to move to the wastewater. On the wastewater side, we have a lot more flexibility because it's not going directly into someone's drinking water. And so if there's a mistake, we look bad, but people don't die. And so we have the ability to try different things, and we have tried different things. And some of those things have turned into standard practice. When I, early in my career, I worked on groundwater cleanups where, they didn't know what to do with volatile organics. Eventually, they figured out, well, if it's volatile, you blow air in it. That makes a lot of sense. But then you're changing it to the air. So you put carbon on it, and then you burn the carbon. So they did lots of different things in wastewater. I'm very encouraged to see work being done on PFOA and PFAS that might allow us to address in situ cleanup, might allow us to do some cleanups. I think we have a lot more ability to work with folks on that side, and you have funders that are willing to do it because we've named responsible parties. We name the airport or the whoever it is, and they need a technology, and they're willing to pay for it. Say, but if there are,
Do you feel like you have the capacity in-house to evaluate these technologies?
I don't think it's ours. I don't think that we should be the ones
Okay.
evaluating the technology.
So you said something interesting about, regulators and, you know, not willing to take risks, and you explained it perfectly, I think, it was nice. One of the issues is, if you're a startup company, and you have a new technology you're trying to bring to market, it requires a tremendous amount of validation.
Yes.
And validation can take a long time, and because we're not, you know, because we're not talking about, you know, two undergraduates with a laptop in the dorm room creating a new, you know, app. It involves a physical system
Yeah.
that is typically expensive and requires years of validation, potentially. And it's really hard to come by venture money to fund that, to support that kind of work. Because the timeline that these venture funds are interested in is to be measured in months, not years. And there's a real disconnect there.
Oh, I agree with you.
And I think that's a big barrier to moving things from the lab into the real world.
So one of the things that, you know, Madelyn asked about is why we don't have research funds. I mean, I think that is.
You don't need the research funds. There are plenty of research funds.
No,
You need,
You need,
development.
technical
Yeah.
evaluation. and-
or, you know, yeah. Validation, things to provide that,
translation.
that from the initial lab to a long enough time that it becomes viable. And I think that's correct. I agree, we don't really need research. What we need is to be able to validate. I'll be blunt, I get calls all the time about, I have a black box. You let me put this on your drinking water or your wastewater, and everything is fine and it's perfect. And I said, well, that's fabulous. All you have to do now is to just tell me, give me the influent data and the effluent data. You do that for a number of years, and you show me that how it reacts in different situations. So, well, I'm not going to give you that. Well, then I'm not ever going to let you use this as a.
I think you just
So
brought,
John-
you brought that to the
Yeah,
core
so
point.
Jonathan, just, you know, what I described, and you know, that project in Salinas, from beginning to end, I think it's about 7 years. You know, with Madelyn and I,
Including the time to select. the site,
Yes,
12
yes.
years.
it's been that long. And so, you know, after everything, you know, you have to prove that it works, and then you have to go through the point of getting regulatory acceptance. And then if whatever you're doing really deviates somewhat, you know, from what is being regulated, then you're in trouble, because in the books, for example, in our case, you have small communities. There isn't something in the book that is really written in terms of how, you know, all the intricacies of what we're bringing in and the technology is going to be regulated. So who is going to, you know, change, you know, the regulation or update it? You know, we don't.
When technology upends regulation, when the technology development, it renders the current system of monitoring inefficient.
Oh, that's a good point.
Yeah.
And
So,
then there's.
yeah.
Yeah. Yeah.
And then
Yeah.
Jonathan, you talked about consistency. Well, I can tell you for a fact that the state certified laboratories make mistakes over and over again. And we have inline monitors, you know, to do a better job. Yet the regulation says that thou must, you know, have grab sampling to do A, B, C, D, and E. Now, I'm not saying it's not good, you know, it's in our case, if we didn't have inline real-time monitoring, we would be able to catch those inconsistencies, right?
So, you know, I don't think that's a bad thing to think about,
No,
but think about who is accountable for it.
right.
That's the, you know, when you have a certified lab, it may be that, you know, they make mistakes 10% of the time. But if they make too many mistakes, they can lose their certification, and someone can be accountable. If your online value makes a mistake, who's accountable? Is it the sensor? Is it the community? Is it the person itself? We have to come up with
Exactly.
accountability.
Exactly.
So less frequent validation by grabs.
Yeah.
Well,
No, you can still do
So-
validation, you can still do, yeah, look, let me put it this way, I'll just say this one thing and then keep quiet, but. You know, everybody at home has all sorts of appliances, right? You have a stove, there are issues about, carbon monoxide, in emissions in the house and so on. Yet, you know, you're not required to do all those very, very complicated monitoring. Why? Because there are systems that are certified and already, and sometimes you have to do periodic checks, like in an elevator that runs here. You know, you have to have a certification once in a while. So we have to think about if all those treatment systems that, you know, David mentioned and I mentioned, that perhaps can be made compact, how do we certify them, you know, so that we can bring them in? Because in a distributed system, you cannot put people 24/7. In our case, the monitoring cost is much higher, the required manual graph sampling is much higher than the operating and maintenance cost.
I will say one thing that I learned recently that I thought was really interesting. It touched on something, I think you mentioned about delivery of water, how much energy it consumes. This is sort of an aside, and it's sort of the vast majority of energy apparently in our water infrastructure has nothing to do with treatment. And everything with delivery, including local delivery, like getting the water from wherever our treatment system out into the distribution system. So it's a real, again, if we're trying to move away from energy consuming processes, we want to really minimize our carbon footprint. That's where we need to do. We need to do lots of these little distributed systems all over the place. To treat water.
That in itself is a reduction of energy.
Exactly.
Not pushing water.
The main way to reduce the energy footprint of water. It's not about the treatment, it's about the conveyance. And
So if I could interrupt you, we need to give Maria a chance to talk about how do we get people to, if we get great treatment done, how do we get people to know that their water was impacted by PFAS? How do we get people then to trust the fact that the treatment works? We have very low consumer confidence in our water here, even though it's very well treated. So how do we get, when you work with communities where you're installing treatment, what are the issues with getting people to actually drink it?
Well, I think the problem is I'm not the right person to talk about this. Because I work in disadvantaged communities with people who don't speak English. And in many ways, you know, I was at the beginning of the idea of disadvantaged communities with SAPA back in Prop 84, and it was a double-edged sword. On one hand, we've managed to get a lot of funding for these communities, and rightly so. On the other hand, they've become experimental labs. Everybody wants to get into disadvantaged communities. I mean, that is the soup du jour. I get calls, and you know, we come and visit your treatment plant in Maywood. And I think we have to get away from this idea of poor people are the ones that they're the guinea pigs. So it would be good to put them, you know, have these discussions in more affluent communities, because I know in the Inland Empire where I live, some of the pushbacks and they're irrational with logistics centers. They're in, you know, poor neighborhoods. Why aren't they in Beverly Hills? And that literally came from a young woman who said, why aren't these warehouses in Beverly Hills? Well, that's irrational because you can't put a warehouse in Beverly Hills. It's built out. What are we gonna, you know? And so the idea she had was valid, that poor people are always an experiment in some way or the other. The idea that you're gonna put them in highly urbanized areas, we can't stick a warehouse here in Westwood, you have no room. So I think, you know, to really understand mistrust in people in general, we need to also look at how affluent communities view their water, not just in disadvantaged communities, because I know in Yoram's project, they're still very leery, you know, and there's nothing wrong with the water. I mean, he has pictures of all of us drinking the water.
But I'm wondering if you're saying disadvantaged communities versus affluent, I think the issue is that affluent communities are not gonna wait, until somebody comes to their rescue. And then you mentioned Beverly Hills, the city of Beverly Hills, there is in fact a desalination plant. Okay, I don't know how many of you know that, but there's a desalination plant,
It's in
because
Santa
they,
Monica.
yeah, and so is it Santa Monica, and
Because
they're
you
not
have-
gonna wait.
Well, yeah, because you have an educated population,
Yes, of course,
so it's easier to explain.
and they have money.
And but it's the money and the education. If I explain something to you, you'll grasp it like that. But explaining it to Roque,
But even if I do, there's no money there, right? I mean, they cannot pool resources, to force a solution.
right,
And they don't have the clout, to be able to force, a solution.
but with the,
Because very simple, they don't pay enough, property taxes.
right, but the
you know,
question
to have
was,
influence.
how do we get people to accept the water? That was the basic question, so in order, that's what I'm saying, is we're always looking at poor people to, it's sort of like the state
Right.
has spent millions of dollars in how to communicate in disadvantaged communities. Literally, I've been paid. The Bureau of Reclamation hired me to write a study for SAPA on how to communicate with disadvantaged communities. Well, guess what? Talk to them. I mean, I don't need a manual. I don't need a manual to learn how to talk to you guys. I mean, we're all human, but see, that's what's happening. It's the disadvantaged communities have become soup du jour. And all solutions are gonna be run through that filter.
I think that one of the take homes though, is that the reason I think that Yoram decided to go and do this project in a disadvantaged community is because if he licensed that technology, no one who bought the license was ever going to serve those communities. They were going to serve the Beverly Hills. And so there's a dilemma. One side of it is they shouldn't be getting fixed. On the other side, if you design a system so that it's affordable to the small communities that are disadvantaged and having unsafe water, how do you do that? So I think that's a good place for us to begin to let anybody else who wants to talk. Go
I
ahead.
have a quick question and then I have to go. And it sort of turns the questions upside down in a way, because hearing all of these, fantastic technology that's available for treating all sorts of quality of water. My question is, I've been working since the summer of 2021 with a multidisciplinary team within UCLA, legal, public health, Greg Pierce at Luskin, trying to assess potential impacts on oil and gas wells, oil and gas operations on groundwater resources and drinking water aquifers. And one of the elements of the regulatory landscape that we're looking at is that there's a whole process by which oil and gas companies can petition for groundwater aquifers to be exempt and to be able to accept discharges of water that's been used, processed water. And the criteria, well, of course, the starting criteria, not that it's the only criteria, but is that the groundwater aquifer is 10,000 micrograms per liter TDS. That's the the threshold. So if it's over that, then you can start this other process.
So if it's over that, you don't even have to do that process. They can discharge to it automatically. It's gotta be between 3,000 and 10,000 to start the process.
Okay, well, there's some additional good information. Thank you. So, okay, so that makes my question even more important, which is why? Because, I mean, when did that threshold, come into effect, and is that appropriate anymore, given the ability to?
So
Treat this
there's a
water.
couple of things to think about.
Mhm.
One is that, when you produce water in California, when you produce oil in California, you produce 9 to 12 barrels of water, for every barrel of oil. That
Yeah.
water is very salty. The reason it's very salty is that, it was marine sediments that laid down to make that oil. So, it's very appropriate to think about what's the best way to get rid of that salty water if you're gonna allow oil production. I'm not gonna argue that oil production is the right thing or not the right thing.
But
But
it's
you,
not just produced water, right? But I believe it's also other water that has many different chemicals and properties.
it's almost all
Right.
produced water. I mean, that is there is a
We're talking
little
about the
bit,
flow back, that's relatively small volume compared to the.
there is well-produced water that they use to, you know.
Right, for
work
well
on
stimulation.
There, we don't do much well stimulation in California. It's, we do a lot in other places, but the.
Sorry, go ahead.
So most of that water is going down into aquifers that are very deep. And had oil in them in the past. Not all of them, most of them. And so I don't, the question is that appropriate? I don't know. What I've told people repeatedly is that we're taking that water that is outside of the hydrologic cycle and keeping it outside. We could bring that into the hydrologic cycle by doing treatment on it and then using that water. We're not creating the water, but we're bringing water back into the hydraulic cycle. It's been out for millions of years. And then you could take the concentrate and put it back down in those very high saline waters. So I think there are opportunities as the price of water goes up for that to be utilized.
But they're not gonna be put back in water that could possibly be used for other purposes.
Why not? If you treat it, these folks.
No.
No, I meant the direct produce water wouldn't go back into a groundwater basin.
Oh, no, it doesn't go to groundwater basins that have, that are used for drinking water or that could impact, waters that are used for drinking water. We spend a huge amount of effort to, make sure that the California Geologic and Energy Management, it's called CalGEM now, they used to be called Dogger, thought that was a better name, CalGEM, we, as the water boards, actually look at all underground injection now because the legislature decided that CalGEM wasn't trustworthy. And so they put us in the co-regulating role. So one of the things we did about that, we said you can't inject, no matter what the quality of the groundwater is, you can't inject produced water into the first aquifer that you find. Because someday someone might need that. And so
Are they
Does
using?
that answer your question?
Sort of, but maybe I can follow up.
Yeah,
later.
When we're drinking wine, I would like to turn it over to somebody else for questions.
Using
Anybody
this
else
water
have
for
questions?
irrigation?
yes, they are actually, mostly on the east side of the Sierras, where east side of the Central Valley, where the oil migrated to really high quality groundwater, and so the water itself is not saline. It's very high quality. They just have to take some of the risky oil out, and then they can use it. Oh, interesting.
So for those of you who are not in science, and I think there's only 2 or 3 of you here, how does knowing this help you in your own work? Anybody? Well, that's something for you to think about.
I guess for me, it's been very instructive to work with not so much the scientists, but the engineers in my work to be able to see those engineering principles, how they can be used to their communities. And I'll give you an example. When I was first starting, I didn't know anything about water. That's not what I studied in school. And the engineers took me to Quail Valley, where they have a septic issue. And we were driving along the roads. I didn't realize those were culverts. And the engineers told me, these are culverts. And it was something that I never would have understood just from being on, being there. And I think that's what's helped me understand my work, is being around people like yourself and being around, people who that is your field of inquiry, that is what you live and die for. So you guys have really helped me in helping those communities, because without the science, without the engineering, it's not gonna work. And back to John's point, if we have to make sure that these communities get safe drinking water. And I'm a consultant, and I work with the Division of Financial Assistance and the Division of Drinking Water every day. And in order to get those permits for the treatment plants, I will stick to my guns with DDW and tell them, I don't want that permit until you are absolutely sure that everything is done correctly, because the state board is under a lot of political pressure. And I know that. And a lot of people try to use that to their advantage, and I actually go against that. I tell them, I don't want that permit until we are absolutely certain that the design is correct, that the implementation is correct, that permit will ensure safe drinking water.
So what you're saying is that you don't want a water treatment system to go into operation before they think that they know that it's gonna work and that there won't be somebody dying.
Yep, because then that's when.
And they're getting pressure to go faster.
Yes, because there's.
Every day.
Every single day. And so he could speak to that, and I'm probably the only consultant that sticks to her guns. And, my clients are big public agencies, and they want speed. And I think that's why they keep me around, because they know at the end of the day, I'm gonna do the right thing, and we're not gonna end up on the front page of the newspaper, even though we have a sativa. But that wasn't my fault.
All right. Well, I've kept you waiting for a long time. I really appreciate you all sitting for 2 hour symposium. And there is wine here and outside. There's non-alcoholic drinks, and there's cheese and fruit and some bread. So I really hope that you stay and chat with each other. And thank you all for coming.
Thank you for putting this.
Thank you.